Okay, we're back on the air, and we are going to talk about where this nuclear energy comes from, and this bridges into our good friend Albert Einstein, who is one of the world's most famous Jews. I have Jewish heritage, so anyway, he does me proud. So Albert Einstein grew up in Germany and left when the political situation was becoming insane and came to this country for asylum and was arguably the most brilliant physicist in all of history. And one of the most interesting things about him is that he was not an experimental physicist. He was a theoretical physicist, which means he came up with ideas and other people tested them, and has invariably been proven correct in everything that he predicted. And he made most of his predictions from extremely simple observations. It's astonishing. Well, anyway, to get back to nuclear energy and the connection with Einstein, his famous equation is E equals mc squared. This is kind of the iconic equation that we are familiar with, but don't generally know what it means. So now we're going to learn what it means. So who can guess what E is? Energy. Correct. Correctamundo. Okay, so energy. Who can guess what M is?
Mass.
Right, mass. Mass. This one's a little trickier. C?
Constant for the speed of light.
Right, the speed of light. So C is the speed of light, which is a big number because light is very fast. So fast that C equals 3 times 10 to the 8th meters per second. That is a long distance, and light goes that far in 1 second. To put this in perspective, light takes 8 minutes to get from the sun to us. So if the sun was extinguished, we wouldn't know for 8 minutes. It would continue to appear to be shining. At astronomical distances, this is a very profound effect. I think the nearest star is like 4 light years away. So the light from the nearest star took 4 years to get here. Yeah, right. A light year is how far light goes in 1 year. Other stars are millions and others are billions of light years away. So the light that we see at night is literally millions and billions of years old. The farthest stars the light from them is about 10 billion years old. So it puts an upper limit on the age of the universe. Now, yes, Michael.
Okay, so when we see stars falling from the sky,
Well, yeah, ask it to the microphone.
when we see stars falling from the sky, I guess like something like a meteor shower, does that mean that it's happening essentially a billion years in the past?
No. That's happening right now, because a meteor shower is a rock falling into the Earth's atmosphere, burning up. It's not something you're seeing far away. However, if you see a supernova, if you're lucky enough to see one, they happen every several thousand years, and they've been seen before. Then the light from that nova could be it's as many light years away as the star is. Okay, so light happens. I mean, light from the stars is quite old. Explodes. Yeah, supernova is when the star blows up. So anyway, we've got this equation, E equals mc squared. Speed of light is a big number. Okay. Now, let's say you got a chunk of material. You got a rock. Here's a rock. It doesn't matter what it's made of. but it has a mass. The mass of the rock is 1 kilogram. Okay? So let's use Einstein's equation. We're going to use the famous equation. Here we go. So the energy of that rock is 1 kilogram times 3 times 10 to the 8 squared. So 3 times 10 to the 8 squared is going to be 9 times 10 to the 16th, if I'm not mistaken. Right? 3 times 10 to the 8, and we square that. So 9 times 10 to the 16th. So the energy is 9 times 10 to the 16th joules. Let's talk about what that means. All right? Here we go. Let's talk about what that means. Okay. All right. So let's say now here's you, and you had your cornflakes for breakfast, so you've got a lot of energy stored up, and you're going to lift that 1 kilogram rock, and you're going to lift it up 1 meter. So let's see here. So you're going to add potential energy to it, 1 meter. So the EP is mgh. So EP equals 1 kilogram times 9.8 meters per second times 1 meter. So how much potential energy did you impart to that rock by lifting it? 9.8 joules.
Oh, right, sorry.
9.8 joules. Okay. So watch this. The rock, it took you 9.8 joules to lift it 1 meter. So if you take 9 times 10 to the 16th divided by 9.8, it's basically 9.2 times 10 to the 15th. What that means is the rock itself has around 9 times 10 to the 15th times more energy in it. So the rock itself somehow has enough energy to lift itself 9 times 10 to the 15th meters. But exactly what? Right, good question. What? What gives? Here's what gives. The energy, this energy that we talk about from Einstein's equation, from E equals mc squared, this is called this energy that is incredibly large inside of all mass has this funny name. It's called the rest energy. And in most cases, this energy is inaccessible. So if you take your mass in kilograms and multiply it by the speed of light squared, you'll find out your rest energy, and it's an enormous amount of energy. I mean, this amount of energy is, hold on, let me look something up. I'll be right with you. Okay, so let's put this in perspective. We're talking about our 1 kilogram rock, and it has 9 times 10 to the 16th joules. And I just looked up on the internet that the largest nuclear bomb ever made, or hydrogen bomb in this case, to be specific, has 83,000 terajoules of energy. So this equals, a terajoule is a trillion, right? 10 times 10 to the 10 times 1 times 10 to the 12. So here we go. terajoule. Anyway, we got to add 12 more zeros is what this comes down to. So there's our 83,000, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And so our total number of zeros is 12, 13, 14, 15. Perfect. Look at that. 83, or 8.3 times 10 to the 16. Almost exactly the same. That's incredible. So the biggest nuclear bomb ever made, has approximately this, it has just a little bit less energy than a 1 kilogram rock. So why is this? How is this possible? Is Einstein's equation wrong? This and much more in the next episode of your physics lecture.